All right, so I did email out a couple of problems for homework. How did that go? Horrible?
Yeah.
Was it really? It didn't go well?
I got stuck on the second one.
You got stuck on the second one? Should we talk about that? Okay, how about we do this? Let's get through this, and then at the end, I'll talk about the homework, all right? All right, so last class, we went over the steps to graph irrational functions, right? And I was looking at our calendar today, and we are behind a little bit. We're supposed to be starting inverse functions today, so we're just about a week behind now, and that's okay, all right? Because I'm spending more time on this than is in the schedule, all right? So last time we talked about rational functions, we went through a whole set of steps, right? There's all these steps to graph these. Do y'all remember the steps? Let's see, step 1, make sure it's rational function. Step 2, find the x-intercepts. How do you find the x-intercepts? Set the numerator, the top, to 0. Step 3, vertical asymptotes. You do that by setting the denominator to 0. And then step 4, horizontal asymptotes. And that was the one where I said there's basically like 3 different scenarios you could run into. And so I wanted to show you an example of each scenario. So we'll kind of wait on that one. Step 5, test points. And then step 6 was using your brain to sketch, right? Okay, so we did this example in class last time. Now, what I was trying to get you to see last time is that when it comes to step 4 in the horizontal asymptotes, the thing that we're going to be looking at is the power that we have on the numerator, or the degree of the numerator and denominator. So we're going to be basically comparing these two numbers. In this problem, we'd be comparing these two numbers, and in this problem, we'd be comparing those two numbers. And I said last time that when it comes to the degree of the top and bottom, you only have three different possibilities. This could be smaller than this number, right? This could be bigger than this number, or these two numbers could be the same. Those are the 3 cases, right? Yes? I mean, there's no other way. If I give you 2 numbers, that's the only thing that can happen. One can be bigger than the other, less than the other, or they're the same numbers. So we have already looked at what happens when the top is smaller than the bottom, right? So when we did this in class last time, what was our horizontal asymptote? When the top is less than the bottom, what did I say it was? I'm crying because y'all don't know. The x-axis, thank you. Okay, so anytime we're talking about a rational function and we get to step 4 where we have to do the horizontal asymptotes, if this is smaller than this, then the x-axis will always be that dotted line that's a magnet that pulls your graph down towards the ends, all right? What we still don't know is what happens in these 2 cases. So today I'm going to cover those 2, all right? And what I'd like to do is start with the bottom one, not the middle one. So we're going to now do this, all right? So I'm going to put the other one over here because I'll need it in a minute. X cubed minus 4x squared over. Okay, so let's do this one. We want to sketch f of x equals x squared minus 4 over 3x squared minus 27x. All right, first step, make sure it's a rational function. It is, right? That's our first step. Second step. Rodrigo. Second step. Okay, so if I'm going to find the x-intercepts for a rational function, I'm going to do what? Set the numerator equal to 0. Okay, Rodrigo, how would you go about solving that? You want to move the 4 to the other side? Okay. So this is a quadratic. This is a quadratic equation. We're missing the x term. So this is one of those special cases. So we're going to move the 4 over. And then what? Square root both sides. Now, very important. When you square root both sides, what do you have to put? Plus or minus. So we actually have 2 answers, right? 2 and negative 2. Is Josh here? Vince. My question to you is, what are these on my graph? Like, what are these going to be when I draw my graph? Because remember, with rational functions, we got all sorts of weird things on the graph. These dotted lines and all this stuff. What are these going to be on the graph?
The X-Intercepts.
X-Intercepts. So are they going to be dotted lines, or are they going to be dots on the graph? Take a guess. If they're X-Intercepts, right, they should just be points, right, that are on our graph. So remember, I like to put under here, at least on these first few examples, these are going to be points on the graph. Your X-Intercepts are always points on the graph. All right? Moving on to step 3. Zeke, how's it going? Were you here last time, Zeke?
Yeah.
You were? Okay. Zeke, what's step 3?
Vertical asymptote.
Okay, and how do we find those?
Set the
Denominator to 0, right? Okay, Zeke, any ideas on how to go about solving that equation? What type of equation is it?
quadratic.
Quadratic, okay. Is it one of the special ones? Like, is it missing a piece?
Yeah.
It's missing that constant term, right? So do you recall how to do that one? I can give you a hint. It starts with G and ends with F. Sorry. GCF, okay? So what is your greatest common factor out of there? What can you pull out of the left side? So what number goes into both of these? It does, 9 times. So 3, and then 1x, okay? And we'll be left with here x minus 9. Okay, and now we'll set both of those equal to 0. So we set 3x equal to 0. We set x minus 9 equal to 0. Zeke, I'll let you finish this up. So here, what's the only number I can multiply times 3 to get 0? 0. Okay, so x is 0. And then over here, we can just move the 9 over, right? And we get 9, positive 9. Okay, so Zeke, we have found 2 vertical asymptotes, right? Now, these are not points on our graph. Okay, these are not. These are these vertical dotted barriers, right? And remember how these behave? These make our function like go like that or like that, right? So these are vertical dotted barriers or wall, however you want to look at it. Okay, that's what those are. All right, moving on to step 4. What is step 4? You know what really bothers me? A lot of things bother me, but like, I don't know how people do this. I don't know. Y'all ever go into like the restroom and someone's got their backpack like on the floor next to the toilet? Like, that just drives me crazy. Why would you do that? It's bad enough putting it on this floor, but God, in the bathroom? All right, step 4 is what? Horizontal asymptotes. Okay, so now this is the step that I have not shown you for this particular problem. Now we are still going to compare the degree of the numerator and denominator. So let's see. These degrees right now are the same, right? Okay, if the top was smaller than the bottom, it would be the x-axis, like the first one we did. But they're the same. And when they're the same, we have to do something very special, all right? So right now I'm going to say the degree of the numerator is equal to the degree of the denominator. Is that okay? Degree of the numerator is equal to the degree of the denominator. In other words, we have 2 equals 2, right? Top and bottom are the same. In this case, and only in this case, you have to go actually look at some numbers. You have to take a look at the number in front of x squared here. What's the number in front of this? 1. And then the number in front of this x squared, which is 3. And you're going to do something with those numbers. You're going to create a fraction out of them. You're going to go 1 divided by 3. So I'm going to put here the line, the horizontal line, y equals 1 over 3 is the horizontal asymptote. This is weird. I understand this is weird. And this is the only time it happens, is when these two are the same. So if this was like x cubed and x cubed, you would be doing the same thing, 1/3. All right? So you remember on the previous problem that we did last class, since they were the same, we just said it was the x-axis. That was your dotted line. Here what we're saying is our dotted line is not the x-axis. It's actually 1/3. So it's like it's moved up. That dotted line just gets moved up 1/3. Does that make sense? Yes? We'll see it on the graph, but I'm just saying it's not the x-axis anymore. Okay, so step 4 good? All right, what's step 5? Sketch and test points. You need test points, but to do it, we're going to do a quick little sketch. So step 5. Here's what I like to do. I like to draw a number line. I like to take a look at the information I have so far. So right now I have x-intercepts where? 2 and -2, is that correct? 2 and -2. I had x-intercepts, which were points on the graph, right? And then I have vertical asymptotes at 0 and 9, right? At 0 and 9. So 9 is way out here. I'm just going to put it right here. Here's 9. I have a vertical asymptote here, so I'm going to draw a dotted line, vertical dotted line. Notice I did not put a point here. Do you see how I did not put a point here? Do not put a point there, because then you might think that's part of your graph, and it'll mess you up. And then I'm supposed to draw another vertical line where?
0.
Through 0, right? Through 0, which is kind of weird because I already have a solid line here, right? So I have to do a dotted line through that. And so what you can do, just so you can see it on your page, maybe just dash them kind of diagonally like that so you can tell it's there, you know? Okay, so this is just to get me an idea of my test points. So do y'all remember where you're going to pick your test points? You have to look at like what you know about the graph. Like we know this point exists, right? So that means you must pick a test point to the left of it. Something over here so you can tell what's happening over here. So what would be a good test point that I could pick here? And notice I'm going to put a little x here, not a dot. What's a good test point over here? -3. Okay, -3. I'm going to circle that. Okay, what would be a good test point between this dot and that vertical asymptote? Something in here. -1 would work. Right there. And then what would be another good test point? Where would we need to be looking here? Between 2 and 9, we need something in here. Okay, so what, 5? Is that all right? You could pick 6, you could pick 7, 8, anything you want. Anything else? Is there any, I guess, region of the graph that we don't know what's going on? Do we know what's happening between here and here? We don't, do we? Right? We know that the graph over here is supposed to go up or it's supposed to go down, right? But all I know is this point, right? So I need some information about what's happening here. So a good test point here would be 1. So the idea here for test points is that you're trying to look in between all the x-intercepts and vertical asymptotes, and on the sides. It's not an easy way for me to verbalize that, like, you know, how you pick your test points, other than always look between x-intercepts and verticals. Always look between those. Vertical, x-intercept, between, right? Between here. But I'm missing, I still need one. One more. Where? Outside, past 9. I don't know what's going on out here, right? So how about 10? I'll pick 10. It's a lot of test points, right? How many test points do we have? 5, right? We have 5 test points. There is a way that you can determine whether or not you have them all. How many x-intercepts did we have? X-intercepts. 2. How many vertical asymptotes did we have? 2. Total of those 2 together is 4. You should always have one more test point than you have vertical asymptotes and x-intercepts combined. Okay, that should always be the case. So if you had 3 x-intercepts and 3 vertical asymptotes, you should have 7 test points. All right, what do we do with these test points? What do we do with them? We test them, but where? What are we testing them? Where are we testing them? Plug it into the function, the original function. So I need to now figure out what's f of negative 3, what's f of negative 1, what's f of 1, what's f of 5, and what's f of 10. And that means you have to plug those numbers into this function right here, this one, the original one. And what we're concerned about, all we're concerned about, I should say, is whether or not the answer that comes out is positive or negative. If the answer comes out to be positive, that tells me my point's going to be up. If it comes out negative, it's going to be down. And that's all I care about. Are y'all with me on that? Okay, so yeah, I mean, this is your life right now. It sucks. Okay, you have to plug in 5 different numbers into the function, all right? So let's try negative 3. Let's go negative 3 right here. So I'll do the first one in detail, but after that I'm not going to show as much detail. Negative 3 squared minus 4 over 3 times negative 3 squared minus 27 times negative 3. Okay, so my numerator turns out to be 9 minus 4, right? Y'all agree? You're squaring the negative, so this is going to be 9, then take away 4, so you have 5 up here. And then the denominator, order of operations, square the negative 3 first, that's 9, times 3 is 27. So you get 27. And then we're going to take away or add this. What's happening here? It's going to wind up adding, right? Because we're going to have 2 negatives here. It's going to become a positive, and that's going to be some number. Who cares what it is? It's, well, I guess, what is it? 81? 81. Okay. Now, we could figure out what this number was, right? On our calculators, we could figure it out. But is it positive or negative? It's positive, right? Because the top is positive, isn't it? And the bottom is a positive number. And a positive divided by a positive must be positive. So do you all agree that when we plug negative 3 in, we get a positive answer out? Okay, so I'm going to go over here to negative 3. And I know that when I plug that in, I get a positive number, so I'm going to put it here. Now, let's try negative 1. What happens when we plug in negative 1? So we've got to do negative 1 squared minus 4 over 3 times negative 1 squared minus 27 times negative 1. And here on top, we're going to get negative 3. And on the bottom, we get like, I think, 30. But what's important to us is that it's negative. So that means at negative 1, I'm going to put a dot below, like this. Y'all following or no? These next 3 I'm not going to show the work. I'm just going to tell you what they are and trust that you can get them, okay? This one is going to turn out to be positive, this one will be negative, and this one will be positive. So at 1, I'm going to put a dot where? Where? Just up, anywhere I want. Okay, so I'll just put it here. And at 5, I should be down somewhere. And then at 10, I should be up somewhere. Now, we're missing one thing. If you look back on our work, we had X-Intercepts, didn't we? And those are on this graph. We had vertical asymptotes. Those are on this graph. We've got our test points. What are we missing? The horizontal asymptote. Now, what was the horizontal asymptote? It was 1/3, right? 1/3? Yes? So what we need to do is we need to imagine that we have a horizontal dotted line, not on the x-axis, but moved up. How much? 1/3, right? 1/3, which isn't very far. So I'm just going to come here and I'm going to mark 1/3 right there on my y-axis. And then I'm going to draw a horizontal dotted line. Yes? Now, am I going to draw the horizontal dotted line all the way across? There's a ruler over here. Let me go get my ruler. Excuse me. Does anyone recall from last class what I said about the horizontal asymptote? Do what? Never all the way across. I told you that explicitly. I mentioned that to you. Never draw your horizontal line, dotted line, all the way across your graph. Only draw it at the ends. Okay, so you may be tempted right now to draw a horizontal dotted line all the way across. Don't do it. What you're going to do is you're going to bring that out, and just out here, past everything, you're going to draw a dotted line. And then over here, same thing. Past all of your dots and points and everything, you're going to draw a dotted line out here. At this point in the problem, we're ready to draw. After you've placed your x-intercepts, your vertical asymptotes, your horizontal asymptotes, and all your test points, once they're there, it's drawing time. All right? Okay, so when we go to draw, I always like to start at the point at the far left. This is the last point on my graph that I know exists, right? That point is on my graph for sure. So you want to imagine that you're going to draw this to the left and to the right. So let's start by going to the left. If I go to the left, what must I do? So what must I do? Does this have any significance? What is this thing? It's a horizontal asymptote, right? And I said it behaves like a what? Like a magnet. This should pull my graph towards it, right? So as I draw this point to the left, I want to draw myself towards that dotted line. So I'm going to kind of pull myself into that line like that. And that's good enough. It doesn't have to be perfect, but you need to indicate that it's flattening out. And it is not, so it's not doing this. It's not like going up, right? And it's not going down. It's going to flatten out. All right, now if we're at, any questions on that? Yes?
What if the dot was like higher?
Okay, good. I'm so glad you asked that question. So the question is this: what if when you drew it, you put your dot up here, right? How would you draw it? Well, you would still go and flatten out to that line, and that would be fine, all right? There's going to be some differences in our graph. And if you go back and remember when we were doing polynomials and we were doing bouncing and touching, right? Or bouncing and crossing, that you might have an answer that looks like this, but then someone else may have drawn theirs like this, And y'all both get it correct because we don't really know how high and low those go. Same thing here. We really don't know, we don't really know how high that point is. The important thing is that it's above the x-axis. That's all that matters, okay? So you draw it and flatten out. Did that answer your question? Okay, so now to the right, where am I going to go? I have to draw out to the right, so where do I have to go? Down to this, right? That's like another point on my graph. So I've got to get from here to here, I've got to draw something between them, right? So I'm going to just curve this down. When I get to that point, what am I going to do? Well, I've got to get to this point now, right? So I'm back in kindergarten connecting dots right now. That's all I'm doing, because there's nothing stopping me from connecting the dots, yes? Just connect the dot, connect the dot. Okay, now I continue to try and draw to the right, and now I have a problem. I'm not in kindergarten anymore, because I've got this vertical asymptote. I've got this barrier, right? And barriers always force us to be up or down. And we talked about this at the end of class last time. It's not like 50-50, you just pick, right? It's one or the other. One of them's right, one of them's wrong. So if I turn up, is that correct or no? Why is this wrong to turn this up? You would cross the x-axis, and you're not allowed to cross. You can only cross here and here. So if I can't go up, I have to go down. So I'm just going to turn this and just make this thing go down like that. That looks weird. I understand that graph looks strange. Okay, now that we've done this, we're going to kind of jump over the vertical and just go to the next point. And then we have to draw it to the left and to the right. So out to the left, Elena? Yes? Are you raising your hand? Okay. I know, but okay, I thought you were raising your hand for another reason. You're good? So this point to the left. What do I have to do? Go up, right? So the vertical is a barrier, forces you up. You can't go down, because if you go down, you cross the x-axis. All right. Let's see. Sylvia? Where now? Okay, so you're going to be connecting dot, and then you're going, down, right? Can't turn back up. You can't cross the x-axis, right? Jump over to the next point. Okay, let's see here. Milena? To the left? Kiana? I don't know your names. Macy. Okay, Macy, you've answered. Kristen, unless you want to. Yeah, why don't you do it? What do we do to the left? What's that? Just go like that? No, go up, right? Because our barrier, right? Our barrier. And then Kristen to the right? Yep, there we go, down to the magnet. There it is. And we're done. Now, I thought it'd be worthwhile for me to actually go to a computer and graph this for us so you can see what it looks like. It was x squared minus 4 divided by 3x squared minus 27x. I think I typed that in right. Okay. Let's see how good ours is compared to the computers. Maybe I'll zoom in just a little bit. All right, so it's hard to see it on the computers, but can you tell where this graph cuts through the x-axis? Can you see the x-intercept? -2, it's actually right there. It's hard to see from the graph, isn't it? Like you could argue that it might be somewhere in here, right? But there's an x-intercept. Another x-intercept looks like here, right? At 2. Okay, and those are the only x-intercepts we have. That matches up with what we have. Now, what happens to the left of this x-intercept? We go up and flatten out, right? Well, this one is just flattening out, so it doesn't have that little hump in it. But the important thing is to the left of this, it's up, right? It's above the x-axis, and it's flattening out to something. We have that. We know that. We can tell it's positive and flattening. To the right of this point, what happens? Function dives down. to the right of our point, what happens? Our function dives down, right? So even though it's like ours is like bumpy and stuff, the main ideas of what the function is doing is indicated within our graph. And then look, the left side goes up and then it goes down like that. So that's this and that, right? And then on the right-hand side, it goes up and out. Yes? So I think our graph, for what it is, without a computer helping us, we have a pretty good graph, right? It's not terrible. All right. So that's an example, another rational function, where you have the same top and bottom, right? So the last case is this one right here. This will be the last example we do, is where the degree of the numerator is bigger than the denominator. So our next test is that right? Thanksgiving is on the 28th, right?
Yeah.
We have a test the day before Thanksgiving? We might move that. We might move that to the Monday before Thanksgiving, not the Wednesday before Thanksgiving. But whoa, wait, hold on a second. Is that really the problem I gave you?
Yeah.
It is?
Yeah. Why is it?
This is not going to be factorable. Let's change that to a -9. Yeah. Everyone got that? We're going to change this to a -9. All right, here we go. First step, is it a rational function? Yes, okay. Second step, X-intercepts, right? Numerator set to 0. Okay, how do we factor that? It's not a quadratic, but we can still use the same methods we've used before. What's that? If there's multiplication, we could set them both to 0. We don't have multiplication yet. How do we create multiplication, though? GCF, greatest common factor. What can you pull out of both of these? X squared. So we factor an x squared out. And now you can set each of those factors equal to 0. So set x squared to 0. Set x minus 4 to 0. So what do we get for that first equation? X squared equals 0. What's the only number you can square and get 0? 0. And x equals 4. Okay, what are these going to be on our graph? What are these? Points, right? These are points on our graph. I'm not going to write it again, but just want to make sure you understand what they are. Okay, so these are points on our graph. All right, third step, vertical, right? For the vertical, we set the denominator to 0. And that's just a standard quadratic, right? That's just your standard old quadratic. And you could either use the quadratic formula or you could factor it doing the AC method. In this case, I'm just going to factor it using AC method. But I will expect that if you were given, no, that's not right. Plus 1 here, minus 1 here. That's right. Oh, no. It's Monday. It's Monday, please. It's negative here. Sorry, it's -8. So x minus 9 times x plus 1. So what are our two solutions from this? 9 and -1. So trusting that you could get to those, right? I'm trusting that you could get to those. And now I'm going to move on to step 4. Oh, what are those? I forget. What are those? Those are vertical barriers. Okay. So step 4, my horizontal asymptotes. So we have not talked about this case, right? This is the case that the only case left, and that is when the numerator is bigger than the denominator, right? So here we have the degree of the numerator is bigger than the degree of the denominator. In other words, 3 is bigger than 2. And in this case, and only in this case, you have no horizontal asymptote. You don't have one. Which means that there is no magnet. Okay, there is no magnet pulling your graph at the ends. All right? So if there's not a magnet pulling your graph at the ends, there's nothing flattening it out, right? Which means that on both ends, your graph is either going to go up or down. Up or down. Kind of like the polynomials, we had like all those different cases, right? Here, same thing. On the left and right, it's going to go up or down. And we have to determine that from our test points. So we're ready for test points now, right? And for the test points, I'm going to draw a number line. Start to draw my graph. So I'm going to put my X-intercepts first. Andrea? Where's Andrea? Andrea? Are you following? You okay? So what should I put on my graph first? Okay, so these, and so I'm going to draw what here? 0 and 4. I'm going to put what there? Dots. Okay, so I'm put at 0 and 4, I'm going to put dots. 1, 2, 3, 4. At 4, I put a dot. Okay. Kayleen? Verticals, and those are going to be where? -1. So I go to -1, and I put a dot. No, dotted line, right? Okay. Like that, and also at 9, right? So way over here to the right. 9. Okay. Done with that. Okay, horizontal asymptotes. Frank? Horizontals, we don't have any, right? So there's nothing to draw there, all right? So how about test points? Who wants to volunteer the test points for us? What test points do we have? Don't talk over each other, please. Raise your hands. 7? What? 7, right here? Okay, everyone agree that's a good test point? All right. How many test points should we have? We should have 5, okay? Because again, we had 2 verticals and 2 X-intercepts. So we should have 5 test points. That's one of them, I agree. Someone give me another one. 10 would work, right? And that's out here to the side. I'll stress this again. Notice I'm putting little X's here, right? Not dots. Why am I not putting dots? Because that might confuse you later, right? You might think that those are points on your graph, right? Okay. Okay, got 2 of them. Another one? 1. I heard 1. Is 1 a good test point? It's between these 2, right? I need to know what's happening between here. I know what's happening. All right, I'm going to be able to use that for this. To the right of this, I know. Go ahead. -1/2. Okay, this is the one that sucks. You can't pick a nice number between here. There's no like nice integer. You have to pick a fraction. So here, -1/2. Right? -1/2. Sorry, it's life. Okay, so to the left of that, I heard -4 from someone. Or maybe that was just the voices in my own head. -4, would that work? -2 would work? -3 would work? Anything you want over there. So I guess the thing you just need to be a little careful with is you need 5 test points, right? If you pick 7 and 8, that's really still just 1 test point because that's between these 2, right? You only want 1 test point between each one. All right, and we get to plug those into the original function, yeah? God, it's going to suck, isn't it? Isn't it going to kind of suck to plug those in? Yeah, especially that half, right? That -1/2, isn't that going to suck? Okay, so let me show you something, all right? It's a slight shortcut if you like shortcuts. But if you don't, if this confuses you, just I expect that you understand you have to plug -4 into there, -1/2 in there, and then just grind it out, all right? But if you want a shortcut, here's a nice shortcut. What you can do is you can rewrite this in its factored form. So just let me do it first. Remember how we pulled a GCF out of that? I could rewrite the top as this. And then I could rewrite the bottom like that. Do you all agree that that's the same function? It's just now factored on the top and bottom. It is so much easier to plug a number into that and determine plus or minus if you look at this instead of this. And let me just illustrate how this works. So let's try -4 first. Okay? So check this out. What is any number squared? Positive or negative? Positive, right? So do you all agree when I plug -4 in there, that piece right there is going to be positive? Yes? So I'll get a positive in the top left. Times, okay, I'm going to multiply times. What if I plug -4 in here? -4 minus 4? What's -4 take away 4? -8, right? So that's going to be a negative number. And I'm going to divide that by, okay, what's -4 minus 9? Positive or negative? Negative, it's -13. Times, okay, what's -4 plus 1? -3, right? So you get negative there. Okay, on the top, when you multiply a positive times a negative, you get negative. And on the bottom, when you multiply a negative times a negative, you get positive. And finally, a negative divided by a positive is negative. So do you see, I can do that whole thing without even typing a single number into my calculator. But I can't tell you what the number is, but I can tell you it's negative. Do y'all see how that's a little faster? Sure? So at -4, what am I going to do? At -4, go down, put a dot. How far down? Up to you. Okay, there. Okay, now we get to do -1/2. This one's going to not be fun, but this should still work. Let's see. F of -1/2. Okay, when I take -1/2 and square it, I still get a positive number, right? Okay. Times, what's -1/2 take away 4? Still negative, right? You're taking -1/2 and you're taking away 4 more. That's still a negative number. Christine? Do you get this, what I'm doing over here or not? Yes, you sure? Okay, I'm just making sure you understand it because -1/2 goes in here, right? So if we take -1/2 and take 9 more away, we should still be negative, right? And what about this last one? This one's just be careful here. -1/2 plus 1. Positive. Positive. So my numerator turns out to be what? Negative, and the denominator is also negative. Negative divided by negative is positive, right? So that means over here at -1/2, I'm going to put a dot anywhere I want above, right? So nobody has asked me whether or not we can just find one, like find the first one and then just make them all switch. No one's asked me if we could do that. We can't do that. Yeah. So thank you for asking. You can't. And I think I mentioned it last class, but just try the next test point. You'll see. It's not going to switch. It's not going to go back to. It's not going to go back to negative. It's going to stay up here. But let's just check it. So if I test 1, let's see what we get. Okay, so if I test 1, well, 1 squared is positive, right? What's 1 take away 4? Negative. What's 1 take away 9? Okay, what's 1 add 1? Positive, right? So the top becomes negative, the bottom is negative, and that together gives me a positive. And so you thought they were going to switch, but they didn't. This one stayed up positive again. Then you check the others, right? You check 7, you check 10. Now, I'll do those for you so we don't have to go through it. But at 7, it will be negative, and at 10, it'll be positive. What do you think? Ready to draw? This one's going to be a little tricky. Let's see. Tiani or Heidi? I'll let y'all both think about it on this one. I'm going to start at the leftmost point and go out to the left. Okay? Thinking about it? Thinking about it? Any ideas on what happens if I go out to the left? So do we have a horizontal asymptote? Nothing's pulling us, right? So what did I say? If nothing's going to pull the function towards it, then it has to do what? It's either going to go like this, okay, like a polynomial. It's either going to go up or it's going to go down. Think it's going to go down? What do you think? Down or up? Down. So why not up? Yeah, if I go up, I'm going to cross, right? So it has to go down. So to the left, it goes down. Right? It goes down. Because we have no horizontal asymptote, it has to go down. Can't turn up because it can't cross the x-axis. All right. I'll stick with the two of you again. To the right. So I'm drawing to the right. I'm trying to just connect dots, right? But there's this vertical barrier. You think it's going to go down? What do you think? Down, right? Again, we can't turn up, right? So it's really strange looking over here, but this thing almost looks like a little parabola over here, doesn't it? It's not a parabola, but it kind of looks like a parabola over there. All right, let's jump over to the next point. Victoria? Yes. Victoria, the next point we have is this one, right? So everything's kind of packed in here, kind of hard to see, but if I draw to the left, Victoria, what has to happen?
If you draw to the left,
Yeah.
start from the point that's right there and then cross.
So I'm trying to draw it this way.
Okay, go up.
I have to go up, right?
Go up.
Okay, now as I draw this way, what
Go
happens?
down to cross through.
I'm going to go to this point, and when I get to this point, what has to happen?
You have to cross.
Do I cross?
Well,
Where's the next point that I have to go to? I have to go back up to that point, right? So it's like I got to connect these dots together, don't I? And when I go this way, I have to go up. So it's going to actually look like this. Up, it's going to come here and bounce off and connect. You'll see that? It's a weird one. And then from there, now, Victoria, you can connect these dots together. So this is going to go like this, 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 and then as I draw to the right, what happens here? It's going to go down because of the vertical barrier. And then I jump over to the next point. To the left, what? Up. To the right, up. Why up? Well, because it doesn't flatten out, so it has to go up or down. Can't come down because the x-axis. This is probably the messiest thing we're going to do in here. I promised you that when we started these, right? Like rational functions are the hardest to graph. That's exciting stuff right there. So I was talking to my other class. Remember that college algebra used to be a class everyone took the same class, right? Are you all aware of that? I told you that in the beginning. Now we've split it up into 2 classes, right? And so this is a class for people who are not going to go on and do more, and there's a class that we do. This, in a regular college algebra class, we spend like 2 weeks on this, all right? Because we make these polynomials, we make them much more complicated, and we really get into like the details of this. But you can appreciate how much work that is required, right? Like if you can't factor, how are you ever going to do one of these, right? So my point is this, like, you sit there and you wonder, like, what is the point, like, of even a person who's going to be an engineer one day, like, why do they have to go through all this when I just went to the computer and had it like that, didn't I? Right? what would be the point? So I'm going to share a quick little story with you about my brother. So my brother is, he went to college for becoming, what did he start? I forget, hold on. Well, he wound up being an electrical engineer, right? So he went to school for electrical engineering, then he went and got his master's electrical engineering. And when he went to apply for his first job, you know, he had his degree, right? And they asked him a few questions, but I'm going to share one of the questions that they asked him, all right? Let's see how y'all do with this. Y'all ready? They didn't ask him to graph a rational function, right? Y'all ready for the question? Pay attention. Two archaeologists walk past a cave. One of the archaeologists goes into the cave, comes out a few minutes later, tells his buddy, I just found the perfectly preserved remains of the first human being. Okay, the question is, how did he know that he had found the first human being? That's the question he had in his that's one of the questions he had in the interview. All right, so let me rephrase the question, or let me state it again. You ready? Two archaeologists walk past a cave. One of them goes in, spends a few minutes in there, comes out, tells his buddy, I just found the perfectly preserved remains of the first human being ever. The question is, how did he know he had found the first human being ever? So if you think you have an answer, I'll let you raise your hand. Anybody have any ideas? Pardon? I want your answer. They didn't ask, I mean, this is an interview question, all right? So what's the answer?
What is that?
Do you have an answer?
It's going to be real long.
Okay, that's fine.
Okay, well, in order to figure out if it's very pristine, you have to look at like a bone structure,
Okay,
and then you have to see whether or not if it was preserved and it was mummified. And
Okay.
then with mummification, you find out how long that process took and whether or not climate was involved in it. But since it was in the cave, I'm guessing no. So if it was perfectly preserved in the climate of a cave, and you can see the bone structure of this person, then you can figure out technically if they were, oh sorry, if they were the first human being or not.
okay. All right.
Where's this cave at?
It's irrelevant where the cave is. Any other answers?
It's 10 a.m.
So what words in the question, what word is kind of in there that seems awkward that I put it in there, but is probably very important that I put it in there? What's that?
Can you repeat the question?
I'll repeat the question. Two archaeologists walk by a cave. One of them walks in, spends a few minutes in there, comes back, tells his buddy, I just found the perfectly preserved remains of the first human being ever. What part of that seems... What do you got?
He's the preserved person?
The what?
He's the preserved human being? You know?
Who's?
The archaeologist who went there.
He's the preserved person? Okay. I'm just looking for answers. Perfectly preserved is the key to this. What does that mean to you? Perfectly preserved.
So is it like not a body? Like is it an actual?
Well, I think it's implied that it's a body, but if it's perfectly preserved, that means it's not bones, right? What's that?
Is it like Jesus or something?
I don't know. I'm going to tell you the answer. I just want y'all to think. Okay, yes? Well, maybe the body was in ice. I don't know. That's not given in the problem. It's just perfectly preserved, right? Perfectly preserved would mean that the body is intact. Ready? Yeah? Okay, are y'all ready for the answer?
Yes, please.
Yeah,
The answer that they were looking for and the answer that my brother gave was that the body was missing a belly button.
Oh, I don't get it.
Just think about it.
Can't be born.
He doesn't have.
The first human can't be born.
Yeah.
Okay? Okay, so what am I getting at? What is the point of that? That's a question that they're asking an electrical engineer, right? For a job. It's not about graphing functions. It's not about, and I realize I'm talking to you and you're not moving on in that field, but it's hard to study this and show you any value to it for what you're doing, but I'm trying to explain to you, like, if you continue to study more and more math and engineering, what you become is a critical thinker, okay? That's what you become. All of this stuff, all these little nuances and details about just everything within math, it forces your brain to just work a certain way. And so that question, my brother got it, I mean, he didn't have to think very much about it. All right, so does that kind of make sense to you? And the other question they asked him was, I can do it with these sticks. I was going to let y'all do a problem in class right now, but I guess we can just do this. It's fun. So let's say we have 10 sticks, all right? They're all identical. They all look exactly the same. Let's say that 9 of the 10 weigh exactly the same. So all of these weigh the same. This one is just slightly heavier. I mean, but you can't tell. Okay, so like, you know, you can't tell that this one's heavier. So if I gave you a scale, like not a scale, if I gave you a balance, okay, you know, like a balance, then how many weighings would it take for you to find the heavy one? What's the minimum number of weighings it would take? That's the key. They said, what's the minimum number of weighings that it would take? Understand? 10 identical objects, one's just slightly heavier. You have a balance. What's the minimum number of weighings that you could do on this and guarantee to find the heaviest one? So, the correct answer, what do y'all think the correct answer is? I mean, you could get it on the first one, right? Like I'm going to mark this one in red. Let's say that's the heavier one, right? I could just grab the first two, not know it, put it on there, and this side would go down, right? And I could have got it on that would be luck. That's not what they want. They want to know what's the minimum number of checks you could do with this scale to guarantee you're going to find this one. You have to, yeah, you have to guarantee that you're going to find it. 10, 5, 9. The answer is 3. Okay? So 5 and 5, right? This side's going to go down, right? Now, what? I've got 5 here, right? Now what? 2 and 2. Put this one on the side. 2 and 2. What's going to happen? That side's going to go down, right?
What if you threw out
Hold on. This is weighing number what?
2?
This is weighing number 2, right? That goes down. Okay. So now it's in here. Weighing number 3. I find it, right? So now, what if this one was down here? Then what would have happened on this weighing? It would have been balanced. That means it's there. 3 is the minimum, though. Okay, how do you get to a point where your brain works like that? You take a lot of freaking classes where you have to think a certain way, right? And then that just becomes kind of a trivial problem in an interview. And so keep this in mind as you're sitting here like graphing rational functions. Like, the end game for you is not to be the supercritical thinker the way this class was originally intended to be, if that makes sense. Just like when I'm in an English class writing a 30-page paper, I'm sitting there and I'm writing it and I'm thinking this sucks, but I'm not going to write papers for a living. You know? That's not what I'm going to do, but I still had to do it. It's just the way it is. All right, so what do you think? We have 15 minutes. Let's do an in-class group quiz. I'm going to give you one rational function to graph. Okay? 15 minutes.